Good evening. I hope you can hear me properly.
Yes, sir.
Okay, we'll get started in a couple of minutes. We'll wait if one or two people might join.
I have doubt in assignment two, one or two questions. Shall I write in chat box, sir?
You have some questions?
No, no. Assignment number two, I'm not able to understand some two questions. Answers for the derived. Assignment is over already. That
Okay, yeah, you can ask me.
they write in chat box.
Good evening. Question number 7, simplex W. So yeah, what is the doubt in question number 7? Hello.
Yes, sir.
Yeah. What is the doubt in question number 7? Like, what is the like
No, that missing entry problem, the simplest data, I am able to understand that problem.
like simplex W one, right?
Yes, sir. Another one is how to find the feasible regions. I am having some doubt. When two equations are given, how to find the feasible regions, sir?
Okay. We'll see one by one. First, let us see the simplex W. Okay. Okay. This is this one minus 11 x1 3/2 x3. So you didn't get the values of A and B, A and C, right? That is the issue.
Yes, sir. Yes, sir.
Okay, then we'll solve this problem. Uh, hmm, so it will be the first thing only, na? So S1.
Yes, sir.
One second. One second. Is it after making the variables, after making x1 and x2 as the basic variables, after that only you will have to find the value of a and c. So we have to do the row operations initially. Did you try doing the row operations like I taught in the last class? In this question number 7, initially you will have to
Where
assume
I'm a doubt how to start. I'm a doubt, sir. Where to start? Some equations are given.
okay, how to start it, that is the
Yes,
problem.
yes, yes.
Okay, then I will show it to you. So you have this problem like z is a maximize this function. So I have told you in the last class that if there is a maximization problem, we'll convert it to a minimization problem. Okay, so we'll convert it to we'll multiply this equation by a negative sign. So you have to maximize this. So what will convert it to? We'll convert it to minus 11x1 minus 16x2 minus 15x3. We have to change the objective function like this. We have to make it to a minimization problem. So we have converted the optimization functions. Now we'll look into the constraints. So the first constraint is x1 plus 2x2 plus 3 by 2 x3 less than equal to 12,000. So we told that since it is less than inequality, since inequality constraint, so we'll add one more this one slack variable and convert it to a equality constant. So what we will do, suppose let us make it s1 equals to 2000. S1 is the slack variable, is the first one. Then the second will be, I think, 2 by 3x1 plus 2 by 3x2 plus x3 plus s2 is equals to 4600. This is a second constant, and there is a third constant also. Half x1 plus 1 by 3x2 plus x3 plus s3 is equals to 2400. And other constants are obviously non-negativity constants, so we'll make the simplex W now. So initially what we decided, initially we have decided that we will take s1, s2 and s3 as the basic variables. Okay,
Yes, yes.
after that we will replace based on the this coefficient, we will replace this s1 which among this s1, s2, s3 we will replace one by the other non-basic variables. So we have s1, s2, s3. Okay, let us make it like this. We will write the equations. So we have x1, we have x2, these are non-basic variables. Then x3 we have s1, s2, s3. We have b, and also we have f. Okay. So initially, what is the first constraint? For the first constraint, we have the coefficient of x1 as 1, x2 as 2, x3 as 3 by 2, s1 is 1, other two are 0. Second constraint is 2 by 3, 2 by 3, 1, 0, 1, 0. And third constraint is 1 by 2, 1 by 3.
How S1 is 1, sir?
S1 is 1 because in this first equation we have taken S1, right?
But it is not 0. Okay.
No, it will be not 0. We are taking it as a basic variable.
Okay,
See,
okay, okay.
initially we are taking S1, S2, S3 as a basic variable. Why? You can see the coefficient of S1 is 1 in the first and is 0 in the other two. So
Okay, okay.
we have seen now what is the property of basic
Yes,
variable.
sir, yes, sir.
So in this way you have to proceed. After that you write the function value. For the function, what are the constraints? It is minus 11, minus 16, minus 15, 0, 0, 0. And there will be, you have to find there is this value is not there. So initially it will be 0. For here it is b is, I think, 12,000, 4,600 and 2,400. Okay, so this is how we proceed here. What it is the minimum one? It is the minus 16. Minus 16. So what x2 will go into this go as the basic variable, and we have to see for which variable it will be there. So we'll take the b with the b by aj, that ratio.
Okay.
So 12,000 by 2, it is 6,000. 4,600 by 2 by 3, how much it will be? I think it will be something 76, 766 something, and
800.
yeah. I think so it will go in the place of S2, I think, right?
Yes, sir. Yes, sir. Yes.
So you replace this, and you will see after replacing the coefficients will be changing. So you will have to match the coefficients as per
Okay,
the
sir.
simplex W, and you can then get the value
Okay.
of B.
Okay. Okay, sir. Thank you, sir. Thank you.
So this is one thing. And
How to find the feasible regions? I mean, there are two equations are there, two lines are there. How to find?
based on the above, okay, above means like it is based on the,
That is question number 10, sir.
yeah, for question number 9 is clear, right? You got the
Ah,
answer.
yes, sir. Yes, I got the answer, sir.
Okay, so for the based on question number 9, the answer is 30x plus 40y greater than equal to 2000, right?
Yes, sir.
So we have
The answer is, I think, 50, 12.5. I got the answer, sir.
okay, that answer is fine now, but the thing is that, yeah, that is
Only for how to find the feasible region, sir. Yes, sir.
yeah, one second. So I will just we'll see the equations first. The equations are 30x plus 40y greater than equals to 2000. Another is 50x plus 40y greater than equal to 3000. So obviously x and y greater than equal to 0. So for the first equation, so if we have to get the line of the first equation, you will need to have the two coordinates at least, right? So we'll find the what is the x coordinate. So to get the x coordinate, what we will do? We will put y value equal to 0 here.
Okay.
We'll put y equals to 0. In that case, what we will get? We'll get x equals to 2000 by 30.
30.
So I don't know what will be the exact value. I think 2000 by 30. I think 3 8 sorry 3 6 20 66 point something.
Yes, sir.
So it will be something 66. And what will be the y value? Like for y coordinate will be, we will put x equals to 0, and for x equal to 0 we will get some y value. What y value will be? I think 50. So one line will be,
Yes, sir.
so it will pass through 66 and 50. And what you see, there is a greater than equals to constant. Greater than equals to means what? That all the values are greater than this line. So based on this constant, all the values will be in the outer part of this line. Okay. Next, the second constant. Second constant is 50x plus 40y greater than equal to 3000. 50x plus okay, I have already written the equation. So for this equation, we will put y equals to 0. What will get x equals to
60.
Yeah, 60 and if x equals to 0, y equals to 50, right? No, I think 75.
75. Yes, sir.
Right? So one is 60 and other coordinate is, suppose we have 75. So this is the summary intersect somewhere here. It is 60. This is 75. So
Yes.
and based on this equation, the feasible region will be greater than this part. So it will be outer region of this. see, now we have to satisfy both the constraints, right?
Yes, sir. Yes,
So
sir.
in the figure, what we can see the region 1. Region 1 is what? Region 1 is this region, right? It is
Yes. Yes.
exceeding this line also, and it is exceeding this line also.
Okay.
So this will be the feasible region.
Okay, sir.
Okay.
Okay. Thank you.
Okay. I hope this is clear now.
Yes, sir. Thank you.
Yeah. Okay. Then okay, we'll proceed to today's class now. Okay, yeah. So in this today's we have a session 3. In this session, we will be covering the contents that were taught in week 3. That is the single value optimization. I'll just brush through the concepts once, and then we'll try to solve some numericals. So the first method of solving single value optimization is the bracketing method. So this is one of the very crude method. Like it takes a lot of time, and for every iteration, you have to do two function evaluations. Like we have to find 2 points. So why do we call it a bracketing method? Because we are trying to get a region where there is a optima will be available. So we'll be trying to narrow out the region from a wide region, and so we will do it in a step by step procedure. So the first method is the exhaustive search method, and the second is the bounding phase method. One second. So the first method is this exhaustive search, and the second is the bounding phase. In the exhaustive search method, what we will do, we will initially take one guess. Like we'll have the 2 points, that is x1 and that is a and b, the endpoints of the interval. We will take one value as x1, that is x1 equals to a. We will take, suppose we want to do, we'll divide the interval into suppose n number of intervals. It may be 10, it may be 20, based on our requirements. So the higher the number of intervals, the more finer will be the region. So based on our requirement, we take some value of n, and we'll take delta x equals to b minus a by n. We'll take delta x equals to b minus a by n. And once we get delta x, we'll then evaluate two other values. One is the x2. X2 will be x1 plus delta x, and then x3 is x2 plus delta x. Now what we will do, after getting the 3 coordinates, that is x1, x2 and x3, we will do the function evaluations at the 3 points, that is at, and then we will see what is the conditions between the 3 functions, the 3 function values. If f of x1 is greater than f of x2 and is less than f of x3, the minimum point lies between x1 and x3. If f of x1 is greater than f of x2 and greater than f of x3, then the minimum point will be somewhere in the region of like beyond x2 and x3, like that. So based on that, we will eliminate one region from each of the iteration, and then we'll finally narrow out the region to one final region where it satisfies the final condition, where we have to meet these conditions. F of x1 is greater than f of x2 and less than f of x3. After till if I get this condition, we'll do the iterations, and then we'll proceed up till we get this condition. So this is the exhaustive search method. This is a type of a bracketing method. And the second method is the bounding phase method. So this bounding phase method, here what we do, we will take an initial guess. Suppose we take one in the interval, we take an initial guess such as x0, and we'll take an increment delta. Delta will be based on a requirement. You can take b minus a by n or something like that. So a delta should not be too large, it should be small. So then what we will see, after getting the value of x0, we will do 2 function evaluations. One is f of x0 minus delta, and other is f of x0 plus delta. And now we will see the conditions. If f of x naught minus delta is greater than f of x naught and greater than f of x naught plus delta, then we can eliminate the region that is outside this region, for if x naught is in this region, and if f of x naught minus delta is less than f of x naught and less than f of x naught plus delta, in this case we can eliminate this region. So we can then after that, once we have got this condition, then we will set x we'll have to find a new point, and the new point will be xn plus 2 to the power n of delta, and based on that we will do the carry out the function evaluations, again do the iterations, and we will do the function evaluations and see which criterion is satisfied. That is, finally we should get the, we'll do the iterations till we get this condition that f of x naught minus delta is less than f of x naught and it is less than f of. So something feasible region will somewhere come here. So this will be x naught, this will be x naught minus delta, and this is. So till we go to this feasible region, we will be doing out the iterations. Just remember, the main thing here is we do the function evaluations at the point where we do the change the point by this formula, that is xn plus 1 is equal to xn plus 2 to the power n of delta. This is the main formula that is involved in the bounding phase method. Okay, so these are the two bracketing methods that are crude optimization techniques. It takes a lot of time, but if we have to solve, like the function is, and yeah, one more thing, these methods are like applicable only to unimodal functions. It is not applicable to bimodal or multimodal functions. Unimodal means there is only one maxima or one minima. So next type of methods are called region elimination methods. So in region elimination, what we do, again here we eliminate the regions where the optima is not available. So the first method is the interval halving method. So the interval halving, what we do, we'll get, suppose we have 2 points, that is x1, x2, and we get a midpoint. Suppose xm is equal to x1 plus x2 by 2. We will do the function evaluations at all the 3 points. Now if f of x1 is less than f of xm, then in this case we can eliminate this region, that is at the right of xm, and if f of x1 is greater than f of xm and greater than f of x2, in this case we can eliminate this region. So we can keep on eliminating the regions one by one till we finally get this condition, that is f of xm is less than f of x1 and f of xm is less than f of x2. Till both these conditions are satisfied, we will carry out the iterations. So so the optimal solution finally will be whatever we get. Suppose if we finally get these points, this is x1 and this is x2, where x1 is a and x2 is b. So the optimal solution will be available at a plus b by 2. That is the midpoint of these two points. Okay, this is, so in interval halving method, what we do, at every iteration, we eliminate 25% of the search area. So we will be eliminating 25%, at 0.25 of the search area in every iteration. Okay, next is the golden section method. So this golden section method is based on searching optimal section based on the golden ratio. I think sir has already taught like what is golden ratio, how to obtain the golden ratio. So the golden ratio is 0.618. So if we have the two intervals, that is the two endpoints of the interval, that is a and b, we will have to get 2 points, that is x2 and x1. And how we will get the x1 and x2? So x1 should be at a distance of tau into L, where here tau is equal to 0.618. Tau into L from A, and x2 should be at a distance of tau into L from B. Then we will do the function evaluations at x1 and x2, and if f of x1 is greater than f of x2, then we will eliminate this region, and if f of x2 is greater than f of x1, then we will eliminate this region, and then the new A and B will be A, x1 will be equal to A, x2 is equal to B, and then again we will, based on that new length, so new length will be suppose L star. Based on this new length, we will again have to find the next x1 dash and x2 dash. Suppose x1 dash will be somewhere here, and x2 dash will be somewhere here. So this will again be based on the criterion that I told, that is x1 dash should be at a distance of tau into L star from x1, and x2 dash should be at a distance of tau into L star from x2, and we will keep on narrowing the region, and after a point of time when the region is satisfies the criterion that they have obtained the optimum that is the region which L star is, suppose the final L star is less than epsilon. Epsilon is our tolerance error. We will set it to somewhere like 0.01 or 0.02. It's very small value. So then we will conclude that the optima will be in that region, and L star will be the optimum length, and between that the optima lies. So
This
this
towel
method
and minus towel can be kept any side, sir.
yeah, can you repeat?
The towel and the 1 minus towel can be kept on any side, left or right.
Yeah. So the towel is like we have to sort of get 2 points, right? We have
Okay.
already have A and B,
Okay.
so we have to get 2 points in the interval between A and B. So the first point will be at a distance of towel from the right end point, and the second point will be at a distance of towel from the like left end point.
So
So
both are towel. Both points are towel from the either end.
yes. So and after getting that, we will be narrowing the region based on that the updated L. L will be updated every time, right? So initially L is between A and B. After first iteration, L will be between x1 and x2. So in that case, L will be getting the sections like narrowing the sections based on this tau into L. Okay. Understood, right?
Yes, sir.
Okay. And yeah, in this method, what we are doing in every iteration, we are removing what 1 minus tau into L of this ratio of the search area, and 1 minus tau into L will be how much? 38.2%. So we are removing 38.2% of the search area in every iteration. So this is a very efficient method. So in interval halving, we saw that we are removing only 25% in every iteration. So it will take more time to get to the optima in interval halving method compared to the golden section search method. So this golden section search is a very efficient and very efficient and economic method for getting a optima. So there is one more method. The third method is the bisection method. In bisection method, what we do? So we already have the endpoints A and B. We will take the midpoint of this interval A and B, and we'll find the derivative at that midpoint. Now, if the derivative is less than 0, then the area between A and Z will be eliminated. If derivative is less than 0, in this case, this area will be eliminated. And if f dash z is greater than 0, then we will eliminate this area. Okay, since if it is greater than 0 means what? Suppose I can show small graphical example. So if the function is like this, so this is suppose z, the slope will be like this. So if the slope is like this, then the slope is negative. So in that case, their optima cannot be in this region. So we can eliminate this region. So optima will be somewhere in the right side only. Okay, optima will be in the right side. And if f dash is greater than 0, means what? The function will be something like this. It is here z is like this, and the slope at z will be positive. So the function will be like this, and in this region the values you can eliminate this region, since the optima cannot be in this region. Okay, so the optima will be in the left hand side. So again we have already one endpoint, and then we get z as the second endpoint, and after that we'll take the midpoint and do the same, iterate the same process. So at every iteration we are calculating only one function value, that is calculating the value of at f of z. So this method is like we are not taking into account the magnitude of the derivative, so it's just taking the sign of the derivative, that is the f dash z is greater than 0 or less than 0. In this method also again 25% of the region is eliminated every time, like in every iteration. Now to make the method a bit more efficient, some people have, some scientists have, what mathematicians have updated this method, and what they did, they tried to consider the similar triangle. Suppose we have x1, we have x2, and we have z. Now they will calculated the they told that we shouldn't take z as the every time as the midpoint of the two values. We can take z based on the function, that is the derivative at x1 and x2. So what they got, they, by using the law of similar triangles, like they took this triangle and the smaller triangle. By taking these two similar triangles, they got that z, we should do the get the value of z like that, so that it is evaluated by this formula, that is x2 minus f dash x2 divided by f dash x2 minus f dash x1 by x2 minus x1. So if we proceed in this way, we can get to the optima faster, rather than just taking the midpoint. Taking the midpoint, sometimes the function may be like, it might have very steep slope like this, so and we are taking z somewhere here. So in that case, like, we will take a lot of time to get to the midpoint. So based on, so this bisection method is updated to get to make it more efficient in getting the optima. So this was the bisection method. Okay, and there is last is the one of the gradient search method. So the gradient search method is based on the finding the gradients, and one method is the Newton-Raphson method. This Newton-Raphson method is a numerical technique to find the roots of a solution. Like suppose if we have a function like this, it intersects like this. We suppose we start at some one x naught, so x naught here. We'll try to get to the root value by this function evaluation. How we will proceed to that? Suppose if we take x naught, then we'll get the x1. So x1 will be evaluated as x naught minus f of x naught by f dash of x naught. We'll do this iteration again and again. So we'll get to x1 such that it will be here, and again from, if x1 is not the root, so again we'll get x2, it will be somewhere here, and finally we can get the root where it is x3. Suppose we are just taking 3 iterations only. So finally at x3 we'll get the root of the function. But for our case, like we are doing optimization, right? We are not concerned with the root, we are concerned with the minima. So when we are concerned with the root, we are considered only in making this function value equal to 0, that is f of x naught equal to 0 in the root, because at this point this is f of x naught in the y-axis and x naught in the x-axis. So f of x naught is equal to 0 when we have the root. But when we are considering this optimization methods, we are not considering, we don't have to make f of x naught equal to 0, rather we have to do f dash of x equals to 0. F dash, why? Because we have already seen in the first lecture that the necessary condition for getting a optima is that the derivative of the function is 0, that is f dash x equals to 0. So we have to make f dash x equal to 0. So how do we get the formula for the Newton-Raphson method? So we'll get the formula based on the Taylor series. I'll just show the small derivation, 3-step derivation, how to get to the this formula. So the Taylor series is given by this. Suppose we have to know the function value at xt. So to evaluate the function value of x at xt plus 1, so f xt plus 1 equal to f of xt plus h into f dash of xt plus h square by 2 f double dash of xt, where h equals to x t plus 1 minus of x of t. Okay. So now to show that what is the condition? The condition is a necessary condition of f of x t plus 1 to have a minimum value is that we should have f dash of xt is equals to 0. So what we will do, f dash of xt plus 1 equals to 0. So sorry, this is f dash of x t plus 1. So we will take the derivative of this Taylor series. So we will take derivative for both left hand side and right hand side. So f dash xt plus 1 is equal to f dash of xt plus h into f double dash of xt and plus dot 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 other small terms. So we are concerned only with the first 3 terms. So because these are enough for getting to the accurate solution, the first order accurate solution. And why am I saying first order? Because here the coefficient of f double dash is h, that is xt plus 1 minus of xt. Since this is power is 1, so we will getting first order accurate solution. If we are going to h square, then means if we take consider till this term, then it is called the second order accurate solution. We are concerned with only the first order accurate solution in Newton-Raphson, so now take only the first 2 terms from this Taylor series and the left hand side. So we will get the final equation as this: f dash xt plus 1 equal to f dash xt plus xt plus 1 minus xt. We have replaced h by this into f double dash of x of t. And what we have to do? We have to make this value equals to 0. If we get this equals to 0, then we can rearrange the terms. Just rearrange the right hand side to get xt plus 1 is equal to xt minus of f dash xt by f double dash of xt. So this is the formula for Newton-Raphson for optimization, that is getting a optimal solution. So don't confuse this formula. Don't confuse this formula with that of the root solution. In the for finding a simple root, it's f of x naught divided by f dash of x naught in the formula. But while doing the optima, it is f dash x naught by x naught or xt whatever divided by f double dash of x naught or xt. So this is the main difference in using the Newton-Raphson method for root finding and for getting optima. Okay. So now sometimes it is not always feasible to directly calculate the derivatives f of f dash and f double dash. So we can use the numerical methods, the numerical calculation of f dash xt and f double dash xt. Like when you are solving this problem in computer. In computer we have to do always the things in we have to apply numerical methods. So numerical methods will be like this. So this is a central difference scheme. Suppose this like I will show you. And we have we have only one value left. So this is xt plus 1 xt minus 1. These are 3 points: xt plus 1 and xt minus 1 in the domain. So the f dash xt will be given, and this is delta x. So f dash xt will be given as f of xt plus 1 minus f of xt minus 1 divided by 2 delta x. The function will be something like this. So this is the for getting f dash xt, and for getting the double derivative it will be f x t plus 1 minus 2 into f of x t plus f x t minus 1 divided by delta x square. So these formulas are also obtained from the Taylor series. You can just go through in a numerical, you can see any numerical like numerical methods book, or I think you might have studied also in your BTech courses maybe. So I won't go into derivation of these formulas. These are well established formulas. So we can, by numerically we can get the values of f of f dash and f double dash, and after we get, we can put it in the formula, and then we can get the optimal solution after the required number of iterations. Okay, I hope this is clear, the Newton-Raphson method. And there is one final method which is called the Fibonacci method, and it is based on the Fibonacci sequence. So what is the Fibonacci sequence? Fibonacci sequence is given by this formula, that is f of n is equal to f of n minus 1 plus f of n minus 2. Now if we take f equal to n equals to 0, so we can't directly use the formula. So the first two values of the sequence are given as this, f not equals to 1 and f1 is equals to 1. So these two values are given, so we can, after that we can calculate f2, f3, f4 like this. So f2 will be, I think, 2 because it is 1 plus 1, f3 will be equal to 2 plus 1, 3, f4 is equal to 3 plus 2, 5, and so on. It will go on like this. It will be the next term will be the summation of the previous two terms. That is how the Fibonacci sequence goes. Now how do we use the Fibonacci method to get the to do the optimization, that is to get the optimal region. So this is also a region elimination method only, like the golden section search method. So here, out of the 2 points in the region elimination, one is the previous point and other is the new point. So we'll start with the two initial endpoints only, that is A and B, and we will have to calculate this x1 and x2. In golden section also we saw that we have to calculate x1 and x2. So this, and then here in golden section, what was the formula to get x1 and x2? It is tau into L. That is, we multiply the length by the golden ratio, it is 0.618. But in Fibonacci method, we don't use that tau into L. Instead of tau, we use a different ratio. That ratio is calculated. Suppose this x2 is located at a distance of Lk star from A. So how do we get the, and similarly x1 is located at Lk star from B. So how do we get the Lk star? The Lk star is given by this formula. It will be f n minus k plus 1 divided by f of n plus 1. Now what are n and k? N is the desired number of function evaluations, that is how many total number of evaluations we want to do. So it can be taken as 5 or 6, like number of iterations, total number of iterations we want to do. Maybe you can 5, 6 or whatever based on your requirement. And k is the iteration number. So in the first iteration, it will be k is equal to 1. In the second iteration, k is equal to 2. Third iteration, k is equal to 3, like that. And we will proceed till k is equals to n. That is the, suppose we have set n is equal to 5, we will proceed till k is equals to 5 from k is equal to 1. We will do 5 evaluations, and after at 5th evaluation we will stop the iteration and we will say that this is the optimal solution. So this is how we proceed. Okay, and so we get Lk star we can obtain. Now we got x1 and x2. So the new length, after getting Lk star, we will have to get a second length, that we will get 2 more points inside that. So in that case, it will be, the ratio will be Lk, and this Lk will be given by this formula, f of n minus k plus 2 by f of n plus 1 into L. So we will proceed the iteration based on this formula, and we will try to get the optimal solution, and we will eliminate each region after this. So this is a step-by-step procedure. I will just this is taken from the book. I will just tell you the steps. Initially, choose a lower bound A and an upper bound B, and capital L is equal to B minus A. Then we set the desired number of function evaluations to be n and set k is equals to 2. Initially k is equal to, okay, sorry for my mistake there. I told it we will start from k is equal to 1. No, we will start from k is equals to 2. The first k will be like just evaluating a and b, so that comes as k equal to 1. So we set k equals to 2. After that we compute lk star by this formula, and then what we will do, we will set the new endpoints as x1 is equal to a plus lk star and x2 is equal to b minus of lk star. So and then we compute 1 of f of x1 or f of x2, and which was not evaluated earlier, and use the fundamental region elimination rule. That is, we set if f of x2 is greater than f of x1, then we will eliminate the region that is to the right of x2. If f of x1 is greater than f of x2, then we will eliminate the region that is to the left of x1. So this is the basic formula of region elimination method, and we will continue this process till k is equals to n, and in every step we will update k is equal to k plus 1. So here also in every iteration 38.2% of the search area is eliminated every time in every iteration. So it is similar to golden section search method. Here also we saw that 38.2% is eliminated in every iteration. Here also it is the same. Okay, these were the
starting k is equal to 2, not 1.
Yeah, starting k is equal to 2, it's not equal to 1. Okay. The thing is that I already told you why we are taking k equals to 2, because the first iteration is like we are taking these endpoints, right? We are taking these endpoints, so this is taken as k equal to 1. So we are doing the second iteration to get the value of x1 and x2. So since we are getting to get the values of x1 and x2, for that it comes as the second iteration for this formula for getting the lk star. Initially we already have L, so when we have the total length L, this evaluation is already, it comes under k equals to 1. Okay, so getting lk star, we do it, we start with k equals to 2. Okay, I hope it is clear now. I can now see through some sample problems. Okay, this is a very simple question. A function is given by f of x equal to x minus e to the power minus x. Find the root of the function between a equal to 0 and b equal to 1 by using Newton-Raphson method. Now we have to find the root of the function. We need not find the optimum. So for finding root, we have to use this formula: f of x1 equals to f of x naught minus x1 is equal to x naught minus f of x naught divided by f dash of. Now f dash x is equals to 1 plus e to the power minus x. So we are taking as x naught equals to 0. So if for the x1 will be equal to 0 minus of, what will be the f of x naught? F of x naught will be 1 minus it is 0 minus e to the power 0 0 minus 1, because e to the power 0 is 1, and this f dash is 1 plus 1. 1 plus e to the power 0 is 1. So it is equal to 1 by 2, which is equal to 0.5. Okay, we have got the first iteration. The second iteration will be x2 is equal to x1 minus of f of x1 by f dash of x1. So it will be 0.5 minus of f of x1. F of x1 will be 0.5 minus e to the power minus of 0.5, and f dash is 1 plus e to the power minus of 0.5. I think this will, if you do the calculation, it will come as 0.567. So this is the correct answer, 0.567. It's a very simple problem. It's like just calculating the function values for this Newton-Raphson root formula, not the Newton-Raphson optimum formula. Okay, we'll proceed to the second question. For a function given below, the upper and lower bound obtained using the bounding phase method. Take x not equal to 0.7 and f of x equal to f of x equal to delta x equal to 0.5 and f of x equal to x square plus 54 by x. Okay, well, 1 second, I will do the calculations. Okay. So in bounding phase, we have f of x is given as x square plus 54 by x. Now, and what do we do in bounding phase? So we have this function, suppose something we don't know. I haven't. This is the like just crudely I am drawing. This is x. We have x, suppose x naught here. We will do the function evaluation at 2 points. That is x naught plus delta and x naught minus delta. We will get these two values and then we will see the inequality, that is the value of the functions at these points. So initially x naught minus delta will be what? 0.7 minus 0.5 is 0.2 and x naught plus delta is 0.7 plus 0.5, it is 1.2. Now we do the function evaluation. The f of x naught minus delta is, you can put x square plus 54 by x, 0.04 plus 54 by 0.2. It is common 270.04. And f of x naught plus delta will be 1.2 square plus 54 by 1.2, 46.4. Now f of x naught minus delta x. Okay, we will do one more evaluation, sorry. And thirdly, we have to do the f of x naught. So f of x naught will be how much? 0.7 square. Yes, 77.6. Therefore, x naught minus delta is greater than f of x naught plus delta. So we have seen that f of this is the inequality. So okay, I'll just, how do we proceed now? Yeah, this is the bisection method. You can see if f of x naught minus delta is greater than f of x naught is greater than f of x naught plus delta, we said then delta is positive. So delta greater than 0. So delta, whatever value of delta that we have, we will set it as positive. Now the second point will be f of x n plus 1 equal to x n plus 2 to the power n of delta. So this implies delta is plus 0.5. So we have x naught equal to 0.7. So now x1 is equal to x naught plus 2 into delta, 2 to the power 0 into delta, and this will be equals to 1.2. X naught equal to 0.7 plus 0.5. So x1 is equal to 1.2. So now we do the f of x1. F of x1 will be how much? 1.2 square plus 54 by 1.2. So this value will come as 46.4. That is already obtained before.
It is 1.2 square, sir.
Yeah, it is 1.2 square. Yeah. Now f of x1 is less than f of x naught, right? Because at x naught we have already seen that f of x naught is 77.6. So f of x1 is less than f of x naught. So now what we do, we set k is equals to 1, that is, and we proceed to step 3, that is we will get x2 is equals to, where k is the power of 2, that is like power of 2 in x1 plus 2 to the power k into delta, which is equals to x1 is 1.2 plus 2 into 0.5. It will be equal 2 into 0.5 is 1, so it will be 2.2. So now f of x2, it will be equals to 2.2 square plus 54 by 2.2. So the value will come as
29.38.
So again we have seen that f of x2 is less than f of x1. So again we will have to proceed to the third iteration or the fourth iteration. So now x3 is equals to x2 plus 2 square into delta. X2 was how much? X2 was 2.2 plus 4 into 0.5. So 4.2, right? Now f of x3 is again what? 4.2 square plus
30.4.
yeah, 30.4. So now we see that this value f of x3 is greater than f of x2. So we stop the iteration, that the optima value lies in between x3 and this x2. So the solution here will be what? One value will be this 4.2, one value will be 4.2, and the left interval will be 1.2. 1.2. Okay, this is 1.2 and 4.2 are the intervals. Okay, now let's proceed to our next question. We need to enclose a field with a fence. We have 500 meters of fencing material with a building on one side of the field where we will not need any fencing. The edges and the maximum area of the field that can be enclosed by the fence. Now the thing is that the field that is we are covering, it is rectangular. This is not mentioned in the question. So suppose there is a house in this side, so we have to only cover the other three sides of the field. So we have to find so that the area is maximum. We have to maximize this area and we have to find the edges, like what will be the length and breadth. Now if we taking it as a rectangle, so if we take this as x, this is also be x, and this length will be how much? 500 minus of 2x. The total length is 500, so the remaining length will be 500 minus 2x. So the optimization function is what? We have to maximize the area. Area will be what? X into 500 minus of 2x. So simply we will get f dash x is equal to 500 minus of 4x. To get the maxima, we will take f dash is equal to 0. This implies x is equal to 125. So this is 125 and this will be 500 minus 250, so it will be 250, and area will be 125 into 250 equals to 31 250. So I think second first option, edges are 125 and 250 and the area is 31 250. A simple problem, there is no issue in this. I think simple calculations only. Again a similar kind of problem. Find two numbers whose sum is 90 and their product is as large as possible. So let us take x plus y is equal to 90. So if one is x, y is equal to 90 minus x, and we have to make their product as large as possible. So f is equal to x into 90 minus x. So to maximize, we take f dash x equal to 90 minus 2x. So we set f dash x equals to 0 to get the maxima. This implies x equals to 45 and y is equals to 40. And how do we know it's a maxima? We take f double dash x is equals to minus 2. F double dash x is less than 0, so it is a maxima. They will get a maximum, and the numbers are 45 and 40. So oh sorry, so not 40 it is 45. 90 minus 45 is 45 only, so it is 45 and 45. Again a very simple problem. Okay, one conceptual problem. While applying the golden section search method to a function f(x) to find its maximum, the f of x1 is greater than f of x2 condition holds true for the intermediate points x1 and x2. Which of the following statements is incorrect? So let us see. We have xl, xu, xl and xu are lower and upper bound, and what we found, f of x1 is greater than f of x2. Suppose we take this as x1, this is x2, this is f of x1, this is f of x2, and f of x1 is greater than f of x2. So the new search region will be in the what? New search region will be in the x1 and x2. So this is a new search region will be in this region. We will have to eliminate this region. We have what? We have to find the incorrect statement. Incorrect statement is the new search region is between XL and X1. XL and X1. So no, this is not true. This will be a region that is eliminated, not the new search region. So it is option C. The new search region will be in this region. Okay. Okay, again a similar kind of question. Consider a problem of finding the minimum of the function shown below. Given the intermediate points at the figure, what would be the search region in the next iteration? So the next iteration, it will be what? The next iteration will yeah, sorry, here the answer will be eliminating this region because it is greater than f of x1 is greater than f of x2. So the new search region will be between x1 and xl and x1. So this is incorrect. New search region is between xl and x1. This is again based on the basic formula of region elimination, that we eliminate region if the f of x1 is greater than f of x2. For the function given below, the upper and the lower bound obtained using the exhaustive search method are take n equals to 20 and f of x equal to x square plus 54 by x. So we have to do the exhaustive search. Okay, let's do like monotonous problem, but still we will do some steps. So 1 less than equal to x less than equal to 11. Now delta x will be what? B minus a by n. So it will be 11 minus 1 and n is given as 20. So it will be 10 by 20, which is equal to 0.5. So we have, suppose we have, what is the method for like exhaustive search? We'll just glance through it. This is the method. We have take x1 is equal to a, so we'll start with a, the lower bound. We take x1 is equal to a, we take x2 is equal to x1 plus delta x, and x3 is equal to x2 plus delta x, and after that will be eliminatory regions where there is the optima doesn't lie. So x1 will be equals to 1, x2 will be equals to what? 1.5, and x3 is equals to 2. So again f of x1 is equals to how much? 1 plus 54, I think it will be 55. F of x2, we will just evaluate this function. And f of x3 is equals to 31. Now f of x1 is greater than f of x2 and greater than f of x3. So the new search region will be what? We'll get x3 plus, we will to add one more point, that is f of x3 plus delta x. Equals to 2.5. Then we evaluate f of x4 is equal to what? 2.5 square plus 54 divided by 27.85. Again we can see f of x2 is greater than f of x3 greater than f of x4. So we are proceeding in this manner. This is x1, this is x2, this is x3, x4, again x5. So we are proceeding in the from left to right till we find that whatever x5 or x6 is greater than the previous value. So the next value is x5 is equal to 3 and f of x5 is equals to 27. Again this value is less than f of x4, so we'll again have to evaluate one more value. It is x6 equal to 3.5, f of x6 is equals to 27.6. Now f of x6 is greater than f of x5. So we will stop the iteration here. So what will be our endpoints? It will be 3.5 and 2.5. So this will be the interval where we will have the optima. So 3.5 and 2.5. I hope this is clear. Any doubts? If you have any doubts, you can ask me.
Taking these 2 points, sir.
Yeah.
Now we are concluding this between 2.5 and 3.5, sir.
We are concluding this. The thing is that, see, I told you, we are proceeding one by one. We evaluated at x1, then we evaluated at x2, we got x3, x4, x5.
Okay.
Till what we got till x6, right? Okay, we'll have 1 second. I will show. Yeah, this is correct. And this is x6 suppose. Okay. So what we got at f of x6. This is f of x6 is greater than f of x5, and
Yes, sir.
f of x4 is also greater than f of x5, right?
So it is the midpoint. Okay.
So it is the it will lie in the midpoint. So
Okay.
we'll just what we do in this method, we just find a region where the this one, that optimum will be lying. So
Okay.
region will be in this region, right, between x6
Okay.
and x4.
Okay.
It the exact value might not be exactly at the midpoint. It may be somewhere slightly near to x5, but
Okay.
x5 might not be the exact minimum.
So it is a region only. Okay.
Yeah, it is a region only. Yeah.
Okay. Okay.
And based on our accuracy only, it will be. So here we took n is equal to 20. So if we take n equal to 100, suppose, then we will have finer regions, but we will have
Okay.
more number of iterations. So in that case, we will get a better region, a smaller region, but we will have the more number of iterations. So it is just like that. Based on your requirement, you can set this n value and the delta value. Okay. So this is the exhaustive search. So we will do one final problem for today. So we will be doing the bisection method only. We have seen the other methods, right? We have seen golden section search, we have seen Fibonacci method. So we will be doing one problem on bisection, and if you can try some problems from yourself on your side at home. If you have faced any problems, you can ask me in the next class also. Before that, we will solve this problem. So here it is given that f of x equals to, sorry, this is, I already 3 into x to the power 4 plus x minus 1 whole square. So this is the what is done in the bisection method we have seen, right? Yeah, this is the bisection method. We will have an interval a and b. We will take z equals to a plus b by 2. We will do with the basic bisection method only, and then we will see with the updated bisection method, like by calculating z in this formula. Okay. So first we will proceed with the initial formula, that is z equals to a by 2, and we'll do the find the derivatives at z. If f dash z we will calculate. Okay, so you have the region a is equals to 0, b is equal to 1, so z is equal to 0.5. So we'll take f dash of z. So how much it will be coming? Into 0.5 q plus so this value comes as 0.5. Now f dash z is greater than 0. What we have seen in bisection method, suppose it is a, now f dash z is greater than 0, so we can eliminate this region, and we will take the new b is equals to z, and then we will take a initial, then a second iteration we will get the z star or z1. Okay, so this is the first iteration. Now in the second iteration, a is equals to 0, b is equal to 0.5, and z is equal to 0.25. Now again we will calculate f dash of z. So f dash of z will be how much? 12 into 0.25 cube plus 2 into 0.25 minus 1, so minus of 2 into 0.75. So it is minus of 1.31. So now f dash z is less than 0. So we will eliminate the region that is to the left of z. So since we eliminate this region, so now a is equal to 0.25, b is equals to 0.5, and z is equals to 1. I think 0.375. So again we evaluate f dash of z. So we get f dash of z, how much it will be the value? 12 into 0.375 whole cube minus of minus 0.375. Again it is minus 0.61. So again we'll eliminate the region that is to the left of z. So the new, again after this, the new a will be 0.375, b is equals to 0.5, and z is equal to 0.4 0.44 will take. So this is till fourth iteration we will do it. So now f dash z is equals to 12 into 0.44 whole cube minus of 2 1 minus 4 minus 0.09. So this value is like f dash z is almost near to 0. So we can do more iterations so that we can get slightly more near to 0, but we can conclude that since f dash z is slightly near to 0, so the optimum value will be somewhere near is 0.44. It might be 0.443 or 445, something like that. So this is how we go to the optimum. Now this was the first method where we obtain z by taking the midpoint. Now we'll do with the second method. Second method is where z is equals, how is z is evaluated? Z is equal to x2 minus f dash x2 by f dash x2 minus f dash x1 by x2 minus x1. Okay. So initially the first iteration will be same only. In this first iteration we will take z equal to midpoint only. After first iteration we will use this formula. So from the second iteration we will proceed. So here a is equals to 0, b is equals to 0.5 and z is equals to, okay. So we have to do the function evaluations at f dash of x. So we have f dash of
equal to 1 now, sir.
what? No, we are taking from the second iteration. Okay, we are taking from this iteration, not the first iteration.
Okay.
So f dash x1 equals to f dash 0 equal 12 into 0 minus 2 into 1 minus 0 is equal to minus 2. F dash of x2 is equal to f dash of 0.5. I think we obtain f dash of 0.5. F dash of 0.5 is 0.5 only. So let us get z. Z is equals to x2. X2 is 0.5 minus of f dash x2 is 0.5. F dash x2 is 0.5 minus of minus 2, so it will be plus 2 divided by 0.5. X2 minus x1 is x2 minus x1 is 0.5. 0.255 2.5. So it will come as, I think, 0.01, I think 0.5 minus 0.1, right?
Yes, sir.
So it will be 0.4. So in this section method we see it's like directly in the third step we are getting to 0.4. Here we got till 0.25 after the second step, but here we are getting directly to 0.4, and we found that our optima is near to 0.4, that is 0.44. Okay, we will get the value of z here also. So f dash z is equals to minus 2 into 0.6. Minus 43, minus 0.43 will eliminate the region to the left of z. So now third iteration will be a is equals to 0.4, b is equals to 0.5, and now we have to again evaluate z. So for this z also, f dash x2 we have is equals to 0.5, f dash x1 is equals to minus 0.43, we already evaluated here, and so z will calculate. Z is equal to x2, x2 is 0.5 minus of f dash x2 0.5 divided by f dash x2 minus of x dash x1, so 0.43 divided by 0.5 minus of 0.4, right? So it is 0.5 minus of 0.05, I think, yeah. 0.05 divided by 0.93, so it will be around 0.44. So directly getting to 0.44 here, and we evaluated the z at 0.44. So we are reducing the number of iterations if we are taking the value of z based on the derivatives at x2 and x1. We are reducing the number since we are getting to this z equal to 0.44 at third iteration only. Here in the initial we went to at least till fourth iteration. Okay. So I hope this is clear. If you have any doubts, what is thought, or any doubts like in general, like from these topics, you can ask me. I'll be here for 5 minutes, and after that we can end this session.
Sir, actually, in a second assignment, there is transport problem, no, sir?
Second assignment, 1 second. Wait. Okay, yeah. Which problem? Hello.
Hello.
Yeah.
Yeah, in that assignment, this transport problem is there, no, sir?
Yeah, question 8 to 11, right? Yeah.
Yes, sir. So, actually, in that question, they have not mentioned anything greater than 2000, greater than 3000. No, so inequality must be less than only, no, sir. That's my actual doubt.
Okay, let me read that. Transport company has two types of trucks, A and B. A has a refrigerated capacity of 30 meter cube and non-refrigerated capacity of 50 meter cube. Okay. While type B has the same overall volume with equal sections of refrigerated and non-refrigerated stock. A grocer needs to hire trucks for the transport of 2000 meter cube of refrigerated stock and 3000 meter cube of non-refrigerated stock. The cost per kilometer is type wise 40 and rupees 50 for type B. So the grocer is trying to rent the trucks to achieve the minimum total cost. Okay, so what is your doubt here? Like, why less than equal to inequality? Like that, yeah, that is your doubt.
3000 no, for
Okay,
product
why it is
B.
greater than equal to inequality? That's the quiz. Like question number 9, you have the doubt, right? Or can you exactly tell me like what is the doubt?
Yeah, sir, give me one minute, I will tell.
Okay.
Hello.
Yeah.
Yeah, sir, in assignment, that the ninth question is there, no, sir, the constraints.
Yeah, yeah.
Constraint in that question, which is actually given, grocer needs to hire trucks for transport of 2000 meter cube only, no, sir?
Yeah.
But in option, it means up to 2000 only, no, sir? About 2000, it is not. How in option, it is given as greater than 2000 and greater than 3000. The correct option is in options there, it has given greater than, both greater than 2000 and 3000.
No, the thing is that when a grocer needs to hire trucks to transport 2000, like it's not the maximum limit. Okay, the grocer, what will be advantages to the grocer? He wants to like transport more of his quantity in its truck, right? He wants to give more and more, so he wants that
Okay.
each truck should at least have 2000 or at least have 3000. Okay, so
Okay,
that will
okay.
be the advantage to the grocer. He wants to like transport more and more in one truck only. It will be less actually more optimum for him. So that is how the problem is formulated, not the upper limit, it's the lower limit. If you keep the
Oh,
upper limit as 2000, then one truck can carry like 10 also or 20 also, right? If the next
okay,
day he
okay, okay,
lost to the grocer, so that is why. Okay.
okay, okay, sir. Okay, sir.
Okay. Any other doubts or anything? Okay, then if we don't have any doubts, we can close today's session. In the next class, if you have any doubts from assignment 3 or anything, we can discuss. Okay. Okay, then
Okay, sir.
bye. Bye bye. Good
Thanks.
night.
Yeah. Thank you, sir.
Okay, welcome. Hello. Yeah, today's session is over. Like, if you have any doubts, I can clarify. If you don't have any doubts, you can leave actually. If there are no doubts, I will close today's session. I am done with today. I have solved the problems. A video will be uploaded. You can go through it and see. Like, if you have any doubts, you can ask later in the next class, next session.